Hi everyone, welcome back to the series on algorithms and data structures for A-level computer science. In the last episode we looked at a stack, so today we are going to look at a queue. So from a conceptual standpoint, a queue is no more complicated than a stack. The only thing that differs between a queue and a stack is the access order. If you remember, with a stack, we had something called LIFO, right? Last in, first out, which meant that if I added A, B, and C in that order, and then I pop from the stack, I'm going to see C, B, and A. So it comes off in the reverse order in which it was added. Okay, a queue is basically the opposite of that. A queue is FIFO, first in, first out. So the best analogy for this is a queue of people. Assuming everyone waiting in the queue is waiting orderly and is considerate of other people, the first person to arrive in the queue will be the first person to leave the queue. Maybe if they're waiting to get on the bus or waiting to pay for something in a shop, the first person who arrives will stand there and wait, and the second person will stand behind them, and the third person will stand behind them, and then they will leave the queue in the exact same order in which they arrived. And that is what a queue is in computer science. Okay, first in, first out. So if elements A, B, C, and D arrive in that order, then they should leave in exactly the same order. Okay, so that is the difference with between a queue and a stack. So let's look at the things that we have here on the screen. So we've got 2 pointers this time. We have a head pointer, which indicates which element will be next to leave the queue. It's the element at the front of the queue. And then we have tail pointer, which points to the back of the queue. So that's the most recently joined element, the one that will be last to leave of the current elements in the queue. We have a couple other things over here. So just like a stack, a queue is implemented using an array. So this is going to represent our array right here. We've got 8 elements, numbered 0 to 7. And then with these pointers, we can enforce the behavior that we want to make it a queue. We have the size here as a variable, just like we had for the stack. Now, for a queue, we're also going to count how many elements are in the queue currently. And there's a very good reason for this that I'll illustrate for you in just a moment. So let's add some things to the queue. So this is the state that our queue is going to be in when it's empty. The head pointer is pointing at 0, and the tail pointer is pointing at -1. Okay. Now there are different implementations of a queue. Sometimes in an empty queue, both the head and the tail are pointing at 0. Sometimes in an empty queue, both the head and the tail are pointing at -1. To be honest, you should be familiar and comfortable with any of these variations. I'm going to include a link to a very good video explaining how queues work in the same course. And in that example, an empty queue starts with both of these pointers at 0. But in this implementation, which I believe is the most straightforward, I'm going to start with the head pointer at 0 and the tail pointer at -1. And this indicates that that the queue is empty. Okay, so if I want to insert A, B, C, D, what I do is I find the position of the tail pointer, I increase it by 1, and I put my value in at whatever position the tail pointer is now pointing to. Okay, so let's add B. So remember the 2 steps. Increment the tail pointer, and then write the element in the right spot. Okay, so that's the process for adding something to a queue. Okay, and that process is called enqueue, like that. Okay, so we're going to write our little stub method. Okay, so that's enqueue. So remember, enqueue means add. I'll put that as a comment there so we don't forget. Hold on a second, I'm going to increase the size of my text so it's clearer for you to see. There we go. Oh, that's better. Cool. All right then. Let's add C and D then, just to finish our example. So remember, let's put these guys over up in the corner so they're out of the way. Down here will be good. First thing, move the tail pointer. Second thing, write the element. First thing, move the tail pointer. Second thing, write the element. Awesome. Okay, so that's in queue. That's to add things. So to delete something from a queue, that method is normally called dequeue. Okay, so just like with a stack, we do not give an argument because the element that's getting removed is predetermined. It's always whatever is at the head of the queue. Okay, so let's just pass for now. And this is going to be the delete method, dequeue. So we have enqueue for add and dequeue for delete. Okay, so if I want to delete something from the queue, very, very simple what I have to do. I take the head pointer and I move it along. Okay, that's it. I +1 to the head pointer. Now, just like with a stack, sometimes what we'll do is we'll overwrite the element that was just dequeued with a blank space to make it clear. But again, we don't have to do that. So I'm not going to. I'm just going to use these pointers to show where things are. And that's actually got something to do with the num elements variable. So we have to actually keep track of what's in the queue and what's not. Okay, cool. So I've dequeued an element. Let me just make myself a bit more space. Let's do 2 more enqueues. So let's enqueue A. Oh, I did the wrong order there. First, increase the tail pointer, then add the element, then increase the tail pointer, then add the element. Cool. Now let's dequeue a couple times. So let's dequeue the B. Let's dequeue the C. Okay. Let's enqueue a couple more elements. Okay, I did the wrong order again there. That's the right order. All right. So let's think a little bit about this scenario that we have here on the screen. Let's think about a very simple question. Is the queue full? The queue is not full. This is the front of the queue, and these 5 elements are in the queue. These 3 over here, A, B, and C, have been dequeued. Now this does not matter, even if I had sort of deleted these values or overwritten them with a blank space, whatever. They're still not in the queue. However, my tail pointer, if I +1, I can't basically. If I +1, it's going to go point to 8. There isn't an element 8, so if I try to add something to position 8, I'm going to get an error, basically. Okay, so I can't do that. However, it would be really wasteful in terms of memory for me not to allow an addition over here. So what I have to do is I've got to enforce what's called circular queue behavior. So I need to have some kind of test to see if I should move the tail pointer to 0, and then I can keep adding elements like this. Okay, so I can add more until the queue is actually full. Okay, so we still follow the same order. So D is still the first thing, E is the second, F is the third, and so on and so on and so on. But we're just kind of wrapping around and using the free space at the front of the array to form the back of our queue. Okay, so we've got to think about the wraparound behavior with the head pointer too. So if I dequeue a couple times, so I'm going to dequeue D, then I'm going to dequeue E, dequeue F, dequeue G, and then dequeue H. Now I've got to wrap the head pointer around to I. Then if I want to dequeue I, dequeue J, dequeue K. Okay. Okay, so let's start coding our queue. So let's do the setup stuff first, where we sort of initialize and declare our pointers and everything else we need. Okay, so we're going to have the size as a constant, and then we're going to have the number of elements. This is going to help us with the wraparound concept. So this is just going to count how many things are in the queue. So every time we add something to the queue, we're going to have to increment this, and every time we dequeue something, we're going to have to decrement it. Okay, we're going to have the head pointer. Now the head pointer, you should be able to tell, is going to point at 0 initially. And we're going to have the tail pointer, which points at -1 initially. Again, you will see versions where the tail pointer is at 0, or you will see a version where the head pointer is at -1. You should be comfortable with any of these variations. Just might mean changing the order in which you do things in a couple stages. Like I said, I'm going to link to a video in the description, which has a slightly different implementation of a queue that you should also know. Okay, so let's think about enqueue. Oh, actually, I'm going ahead of myself. Let's actually create the queue first. Okay, so the queue is, I'm going to call the list that we're using for the queue, queue. Okay, so this is going to look exactly like how we declared the stack. Okay, so now at this point, if I run that, let's just check we've got the right thing. Oh, got a mistake here. Oh, my variable name. Okay, try again. And let's look at the queue, and you can see it's just like an empty, a list of empty strings. So that looks good. So let's turn this list into a real queue. So we'll start with enqueue, and let's give ourselves global access to the head pointer, the tail pointer, and the num elements counter. Okay, because remember we're going to change some of these things. So when we enqueue something, let's think about our exceptional cases first. So the basic actions for enqueue are increment the tail pointer, and then write something to whatever the tail pointer is pointing at. When can we not do that? So we can't do that when the queue is full. Okay, if we've got 8 things stored in our queue, in this case, because my size is 8, then I'm not going to allow this function, this procedure, to try and add something else. So let's deal with that scenario first. So if number of elements is greater than or equal to the size, okay, then let's just print a error message. So let's do unable to add new data because the queue, I can never spell queue. I know how to spell it, but I find it very hard to type it. Just something about the muscle memory isn't right there. Okay, let me just pull this over. Okay, so that's us dealt with our exceptional case. So how do I add to the queue? So really simple, tail pointer equals tail pointer plus 1, right? So that's this behavior. I'm moving the pointer over to point to the next empty element. Okay, and then I need to just do queue tail pointer equals new data. So new data is the argument that gets passed to this procedure. So I'm saying in the queue at position tail pointer, let's write our data. And we've also got to keep track of the number of elements. Num elements equals num elements plus 1. Okay, and then let's print a little success message. Added new data to the end of the queue. Excellent. Okay, so this is almost good. We just have to think about the wraparound scenario, right? So when do we want to wrap around? So in this case, when the tail pointer is at 7, or maybe size minus 1, we want to move it back to 0. Okay, that's basically the situation. So let's add that in. Let's do it right here. Okay, so we do if tail pointer is greater than size minus 1, then we do tail pointer equals 0. Okay, that's enqueue. Great. So let's run this and see what we have. Okay, so let's just double check our queue. Yep, our queue is there. Let's enqueue a couple things. Oh, and let's check the value of our pointers actually. So let's do head pointer 0, tail pointer minus 1. Okay, everything's fine. So let's enqueue something. Let's enqueue A. Okay, we get our success message B and C. Okay, let's take a look at our queue. All right, so you can see everything's in the list. Let's take a look at our pointers. So what's our head pointer right now? It should still be 0 because we've not removed anything. Okay, and what should our tail pointer be? It should be 2, right? Because our last element C is in position 2. Okay, so let's keep adding things and let's try and fill up our queue. Okay, this could take a while. Oh. Sometimes that happens with idle. Okay, where are we? Okay, got space for one more thing. H. And then if I try to enqueue I, hopefully I'll get an error message. Unable to add I because the queue is full. Fantastic. And if I look at queue, you can see it was not added. Let's check our pointers. So our head pointer should still be 0, and our tail pointer should also should be 7. Sorry. Okay, now let's take a look at DQ. So just like enqueue, we need to have global access to our pointers and our element counter. Okay, so let's think about the exceptional situation. So remember, all head pointers do is basically head pointer plus 1. When would we not want to do this? When would we not want to allow the head pointer to plus 1? Well, surely if the queue is empty, then we don't want to do this, right? So that's going to be our exceptional case, so let's deal with that first. So you can say if number of elements, let's do less than or equal to 0 just to cover all eventualities. That means the queue is empty. So let's say cannot dequeue because the queue is empty. Okay, else we can proceed with our normal behavior. So let's capture the element that's getting removed. So if I dequeue in this situation, I'm removing the item at position 0. So let's do removed equals queue head pointer. So now we've got a copy of what we're deleting, just so we can print that later. And then we want to do head pointer equals head pointer plus 1, right? Because I'm going to move it over here to the right. Also, I've got to reduce the count -1. Okay, and that's pretty much everything. Let's do our success message. Removed, and then we can show what we removed from the queue. Okay, so we have one more thing to think about, and that's the wraparound behavior, basically. Okay. So if you can imagine like this situation, okay, where we've got 4 elements. We've got one here. Let's type something in actually just to illustrate it. We've got A, we've got B, we've got C, and we've got D. In this situation, if I dequeue A, there's still some things over here, and I need to wrap this around. Okay, I need to wrap this around. So after we've increased the head pointer already, right? So we've dequeued A, head pointer is now 8, okay, which is invalid. So we need to pick up on that basically. All right, so we can say if head pointer greater than size -1, then we're going to set head pointer to 0. Okay, so it's going to move all the way around like that. Okay, and that might be everything. Let's give it a test. Okay, actually, just for testing, I'm going to reduce the size to 4, just so it's easier and quicker to fill this up. Okay, so let's look at our queue. You see we've got 4 things this time, so it's in queue A, in queue B, in queue C, in queue D. Okay, now our queue is full, as you can see. So let's try to enqueue E, and we should hopefully get an error. Cool, let's check out what our pointers are doing. Okay, they're in the right place. Let's dequeue something. Okay, so you can see we're moving A and B. So that's the same order in which we added things, right? But you can see they're not actually being deleted from the array. But moving the pointers is enough to delete them logically from the queue. So what's our head pointer? Head pointer should be 2 to point at C, and our tail pointer should still be 3 pointing at D. Now let's enqueue something and test out our wraparound behavior. Okay, so we've added E to the end of the queue. Let's look at our queue, and you can see E has wrapped around and gone in this position, but it's still at the end of the queue because our tail pointer should now be at 0, and our head pointer should be at pointing at 2 for C. So we've currently got C, D, and E in our queue, but we've got this wraparound behavior. Let's enqueue F. Let's try and enqueue G. This should fail. Yep, unable to add G because the queue is full. Okay, let's dequeue. Let's dequeue. Okay, and then let's dequeue again. Okay, what's our head pointer at now? It should be 1. Yeah, tail pointer should be also 1. Dequeue. Now our queue is empty and this should fail. Can't dequeue because the queue is empty. Let's add something else in. I can't remember what letter we got to. Cool. So I'm pretty confident that this works well. Do observe the fairly extensive testing that I'm doing. I'm trying all the different kind of scenarios. I'm filling up the queue, then deleting something, then filling it up again, then deleting it completely, then trying to add something, trying to delete when it's already empty, trying all these kind of possibilities. That's the best way to test things, basically. Okay, so that's everything for this video. We have coded the queue, so you'll be able to find the code for this example as a replit link in the description to this video. Also in the description, there is a link to a slightly different implementation of a queue that you can check out as well. We will look at some exam paper examples in a future video for all of the data structures and algorithms in this series. So that's everything. Let's finish there for today. Thanks for watching, and I'll see you in the next one.